In this video lecture, we'll look at visual illusions. First, we'll consider Helmholtz's unconscious inference theory and how it can explain some size illusions. And then we'll look at a couple of illusions that are based on perceptual constancies. Hermann von Helmholtz proposed an unconscious inference theory of perception many years ago in the 19th century. In his theory, there were three steps to perception. First, we unconsciously analyze cues in the sensory input. Then we construct a perception that includes depth, size, and motion. It's important that our perception includes this information because the size of an object very much depends on its depth. As objects are further away from us, they appear to be much smaller than objects that are close to us. If I want to determine the size of an object, I need to know how far away it is. After we've determined depth, size, and motion, then we send that perception to the conscious mind. If the brain makes a miscalculation in terms of how far away something is, it can lead to what we call a size illusion. The Mueller-Lyer illusion is a classic size illusion. If you look at the green line and the red line in this display, most people find the red line to be longer than the green line. In fact, the two lines are exactly the same length. Helmholtz explained this illusion by considering the depth information that's present in the displays. If we look at the top line here, we can imagine that this is sort of like looking straight down on a rooftop, where this is the peak of the roof and these are the two eaves going down the side of a house. The second display is the opposite. This is what you'd see if you were looking straight up an attic at the roof line from inside a house, where this is the very top of the roof and these are peaks from the inside of the house. The two lines actually take up the exact same amount of space on the retina, so the brain knows that relative to each other they're the same size. What the issue is that the brain determines that this line, the green line on top, must be closer to us than the red line on bottom. All things being equal, that is, the size of the lines being equal, if this object is in fact further away from us, our brain determines that it must be longer, and we end up perceiving that line as being longer. Helmholtz's theory can explain a number of size illusions, but there are some issues with it, in particular as it relates to the Mueller-Lyer illusion. These are all examples that are very similar to Mueller-Lyer, and each produce a similar result. In the first one here, we don't actually have the solid lines, yet people tend to perceive the top line as being longer than the bottom line. You might argue that these dots actually provide the same kind of information as lines concerning the distance that these two lines are from us. But if we look at the next one over here, it's very difficult to make that same argument. Again, people find the top line to be longer than the bottom line. However, it's hard to imagine that the brain would determine that this line must somehow be further away from us than this line. The bottom one is probably the strongest example of all. Most people see the gap between these two corners as being longer than the gap between these two corners, but in fact they're exactly the same size. And what makes this a particularly striking counterexample against Helmholtz's explanation is that there is 3D information available there concerning distance, but from the brain's perspective, the distance that this gap is from you is exactly the same distance away as this gap. So it doesn't really explain this particular illusion. It does a better job explaining size illusions that are based on linear perspective. So here we have two balls. Again, this one appears to be larger at the back, but they're actually the same size. Here we have lots of information in the stimulus suggesting distance. And so what the brain is determining is we have two balls that are exactly the same size. However, one of them is much further away than the other. Therefore, the one that's further away must be larger. It also explains the Ponzo illusion. This is a classic visual illusion. Most people find the top line to be longer than the bottom line when in fact they're the same length. But there's linear perspective in these railroad tracks that make the top line appear to be further away than the bottom line. Since they're exactly the same length, in terms of how much space they take up on your retina, the brain decides that the one that's further away must therefore be larger. Other size illusions are based on what we call perceptual constancy. Perceptual constancy is the idea that an object doesn't change just because environmental conditions changed. For example, we all know that a tabletop is rectangular and that the corners are all at 90 degrees. But if you move around a room looking at a table, its shape actually changes on your retina. However, your brain knows that the table isn't physically changing size, it's just that you're looking at it from a different perspective. And so we have what we call constancy for perspective, the idea that an object doesn't change its shape when you change your perspective of looking at it. And this can lead to illusions as well. So if we look at the two rectangular boxes, it's hard to imagine, but in actual fact, the box on the left, if you were to rotate it about 90 degrees, is exactly the same shape as the red top on the box on the right. I can demonstrate this by selecting this box, and I'm just going to rotate it 90 degrees, roughly the same orientation as the other top. We'll slide it over, just adjust it a little bit here, and you can see that it fits directly on top. These two shapes are exactly the same size. I can spin it back and get it to the right orientation, shift it back to this top. Again, just make a little adjustment and fit it on, and you can see that it again fits back on this top. It's quite a striking illusion because it really does appear these rectangles are different. It's only by confirming their shape that we can actually convince ourselves that they are the same size. This illusion extends beyond the tabletop. This is the exact same illusion, except there's a picture of a person on the top. If you compare, you'll notice that this person actually seems considerably thinner than this person. Again, they're exactly the same picture, the same image, and the same shape. Another constancy is brightness constancy. Our brain understands that just because something is in a shadow or is in bright light, the object itself hasn't changed. It's the same brightness or the same color. So for example, if we look at this chess table here, you'll see that the column is producing a shadow that falls over several of the blocks. Our brain knows that even though that block B is in a shadow, that it's still lighter than the surrounding black box. But this actually creates an illusion. You'll see the other square labeled A up above here. Believe it or not, square A and square B are exactly the same shade of gray. There's no difference between those two. I'll try to show it to you here by laying over a solid gray bar. If we compare B and A to these two sidebars, you can see that they are exactly the same shade, and in fact the same shade as this square down here. If I just remove that bar, you can see again they look to be different, but when I place that on, we can see that they are actually the same shade. What the brain has done is it's made this darker square appear lighter in our perceptual experience, because the brain knows that this is a white square and this is a black square, and simply because this square is falling under a shadow, it hasn't changed its true brightness. This would be a good time to read the Ramachandran article in Scientific American Mind that's included with this module called Sizing Things Up.